day at the school. Dr. Smith's going to continue with his lectures on quantum mechanics now.
Okay, so let me just remind you where we got to yesterday. So what we did was we defined the path integral. So the notation we ended up with was, well, so this was the amplitude we wanted to calculate. Remember, for a particle starting at position qi, evolving for time capital T, and then it was the amplitude that it would end up at position qf. And we did that by summing over all possible paths from qi to qf that took time capital T. And the notation we had then for that was this integral over all paths q of e to the I over h bar, and the action which we evaluated for each path. So you pick a path q of t, and it's not explicit in this notation here, but it should be a path that starts at qi, finishes at qf, and takes time t, and you put that into the action, and that gives you the contribution from that path, and then this integral means you sum over all possible paths that satisfy that. And to make sense of that, we've derived it as this limit. So the idea was we took a continuous path and we split it up into time intervals of a short time delta t, and the precise limit. So I should say usually you don't need to bother. Usually a lot of things you do just involve the idea of this path integral. But if you want to do precise calculation, then you often need to go back to this derivation here. So we'll do one example later on. So let me just write in all the factors. So it's 2 pi h bar delta t to the n over 2. And then we've got n minus 1 integrals. And the thing we integrate is exponential I over h bar sum j equals 0 to n minus 1 delta t times the Lagrangian evaluated at qj dot. Okay, and well, with this notation, what we mean by qj dot, it's just qj plus 1 minus qj over delta t. So obviously when we do take the limit n goes to infinity, where delta t is the time interval capital T over n. So when we take that limit, delta t goes to 0, and this does become the derivative. So I've used that notation. And the q1 up to qn minus 1 are just intermediate steps after each short time interval, and we integrate over all possible values of the path at these intermediate times. And we start, of course, so q0 is identified with our initial position, and qn is identified with our final position. Okay, so that's a basic summary of what the path integral is, and this thing here tells you precisely how you would go about calculating it if someone gave you a specific Lagrangian. You could try and calculate this. And we'll see an example later on where we do actually calculate this. Okay, so that's just a summary then of what we did yesterday. Yes, sure. Right. Yeah, good. So, okay, maybe I should slightly explain then. Yeah. So, what I said with the screen was not absolutely identical to this, because, as you say, if I have these screens, I start at some point here, and I take all this, right, and so on, and then we end up somewhere over here. So say you just want to find the amplitude it gets to here. So this would be my initial coordinate, my final coordinate, and somehow it goes through, that's right, all the different paths it could take, all various different combinations, sum over all of these. Now, that's right, I take a lot of these screens. Now, in this diagram here, really I'm thinking of something like, and that's like a two-dimensional diagram, so it's flowing from here over to here. And I'm putting these screens in at fixed positions, say in this y-coordinate. Now, more precisely what I'm doing over there, I'm somehow putting in the screens at given fixed times, and then I'm asking the same question. So what's happened here is, that's right, so the separation between the screens and time is this delta t, which obviously just splits up the time interval. So this you should think of here, t equals 0, going through to t equals capital T, and that's that limit. And yes, I put lots of holes in these screens, and putting in lots of holes means that I sum over all the given intermediate positions. So in a sense, there's two limits, but one limit just gives us a straightforward set of integrals, and then the other limit isn't done yet explicitly here. So the limit that was still to do there is the one where I put in more and more screens to fill up all the space in between, or all the time. Right. Well, yes. So the idea of whether this converges is, of course, is another issue. So it's what I've done. In fact, yeah. So what I've done here is, so it's not obvious from what I said here whether this converges, whether it really makes sense. Because remember, what I did was I said, yes, so if we looked at two short time intervals, so let's so you could imagine this sort of thing. So this is however I want to split up my screens, so I haven't done that yet, and they're still separated. So this is two neighboring screens, if you like. Now, what I'm saying is, if it passes through any point here, then any point here, then somehow I'm summing over all the paths. But of course, one thing I've said here is I've taken this q dot to be a difference of the q's over delta t, and in fact, what I've summed over, of course, is all sorts of paths. So I've summed over a path where particle goes through here, and then it goes through that point down there. And of course, because I'm integrating, so some of the neighboring q's, because I integrate over the full range of these q's, then of course that derivative isn't necessarily well defined. So what I'm integrating, I've got all these jaggy shaped paths. When I take the limit, I'm not guaranteed to get smooth paths. So it's a very tricky issue to really say precisely how well defined that thing is there. So really, you sort of take it as this sort of definition, and, well, when we go on to do field theory, then you don't integrate over all the paths, you integrate over all configurations of fields. And what you're basically relying on is somehow the fact that very badly behaved things should give a large contribution here, in a sense that we'll try and make a little more precise in a minute, and don't really give any contribution overall. So somehow so if rather than an I here, if you imagined a minus in here, then when this goes very large, it's exponentially suppressed. So very jaggy, badly behaved paths, you hope, give very large contributions up in an exponential with a minus sign and get suppressed. And we'll see how that works in the case when I actually have this I here just in a minute when we take the classical limit. So it is a difficult issue, and in general, I mean, people have looked in more detail on this. And I think this, for quantum mechanics, it's reasonably well defined, the path integral. When you go to field theory, I think, strictly speaking, it's just a formal way of doing something. But the way you do it agrees with other methods. So it's kind of an empirical thing. You do a calculation one way, and then you do it another way, and you don't really have any strict mathematical reason for believing you've done it exactly correct. But you get the same answer whichever way you do it, so you kind of believe it and trust it. But who knows, because you can only explicitly do it exactly, of course, for very simple cases, and maybe that's the reason it agrees. So, yeah. Okay, so let's see what we do now is okay, so what I want to do now is see how, so just look at this expression here and think of this as some sort of sum over all possible paths, Q of t. And each one comes with its own amplitude, which is e to the I over h bar times the action. Now, of course, one thing you should get out of quantum mechanics, you should be able to take some limit where you get classical mechanics. So that's the obvious question to ask. How would you get classical mechanics from this sort of thing? So in classical mechanics, there's a very special path that you take because you've got some equations of motion and the particle follows a particular path. Now, in quantum mechanics here, we're summing over all possible paths. So these look like two very different ideas. So how do you go between one and the other? Because you believe that fundamentally you've got a quantum theory, but when you go to looking at large scales and some appropriate limit, that we don't usually care about quantum mechanics. If you throw a ball across the room, I don't sum over all possible paths that it started here and ended up over there. I would just say it would follow some parabola. So how do we get that from here? So this is undertaking classical limit. Okay, so the first problem is, if we think about it, the sum over all paths. Now, what we'd imagine is maybe the classical path gives a huge contribution compared to everything else. And so mostly the contribution comes from classical path. But that's not right, is it? Because there's an I up here, so it's e to the I times some real number. So it's just a phase. So it's something in the complex plane, this thing here lies in the unit circle. So every path contributes something with magnitude 1. So every path, the magnitude that's contributed to this sum is the same. So this is an important point. So this is not what happens. Okay, so from the starting point of view, just naively looking at this, you think that all paths are somehow the same because they just all contribute to some phase. So they all contribute with magnitude 1. Or, well, at least with equal magnitude, because obviously there's some overall factor hidden inside what I mean by that sum over paths. But they all contribute equally. So how do we get classical mechanics from that? So what we do to get classical mechanics is, let's look at what happens if we have the classical path in here. So perhaps it's worth just giving a brief overview. Right, so the action we get as an integral over time of our Lagrangian like that. Okay, so Is everyone familiar with how you